Okay. Now, in the previous hour, what we had studied was when we have this interface, we send light straight to the perpendicular to the surface. Well, that is one special case. In general, you will just send it with an angle. Now let's consider that case. What happens when we send the electromagnetic wave at an angle? This is my interface. Again, this epsilon 1, mu 1, epsilon 2, mu 2. I will be sending my electromagnetic wave in this direction. This is my K. Now, of course, there are two possibilities. Now, if you just think of this, this is my K vector, this is my electric field, this is my magnetic field in the wave, these three fingers. Now, when I am sending it to my surface at an angle, I can still keep the B field parallel to my surface. I can rotate my wave around the B field. So a B field stays parallel to my surface, but the electric field is no longer parallel to my surface. Or I can consider a rotation, I can rotate my field around the E field. In this case, the E field stays on my parallel to my surface, but now the B field is no longer parallel to my surface. So these two cases, they behave differently in terms of their reflection properties. Now, of course, in general, you will just send it some arbitrary direction in which neither the E field nor the B field will be parallel to your surface. But such an arbitrary wave, you can always write it as the sum of two waves. One has the electric field parallel to the surface. One has the B field parallel to the surface. Now, as an example, we will just consider the case when the B field is parallel to the surface. So the electric field is in this plane of the screen, so-called the reflection plane. So this is my E field. Let me call them K1. And where is the direction of the B field? Out of the screen. This is my B1. Now this wave hits my surface and then some of it will be reflected. Well, the reflected wave will be moving, let's say, in this direction, K1 prime. And the electric field, this is my electric field E1 prime. What is the direction of the B field? Into the screen. B1 prime. It's into the screen, and some of it will be transmitted. Let's say, just for sketching purposes, let's assume this is my transmitted wave. The electric field will be perpendicular to it, E2, and the B field will be perpendicular to both of them. It will be perpendicular to this plane of incidence. It is B2. Now, on the left-hand side, the electric field, the total electric field on the left-hand side will be, let me use E10, whatever the direction is, times e to power I K1 dot R minus omega t plus E10 prime e to the power I K1 prime dot R minus omega t. This is the electric field on the left-hand side, and there is the electric field on the right-hand side. This is E20 e to the power I K2 dot R minus omega t. So these are my electric fields. Now, what are my boundary conditions on the electric field? We had already derived them. You see, these conditions, the first line and the third line, I said that they are valid in any case. We didn't make any assumption about the direction of the incidence of our electromagnetic wave. to derive these boundary conditions. The only thing we assumed was that there are no free charges. As long as there are no free charges, there are no surface charges, no surface currents, these boundary conditions should be satisfied for an arbitrary surface. Not necessarily on the surface between two different media, but just imagine any mathematical surface. For that mathematical surface, these conditions should be satisfied. It should also be satisfied for this case. Well, let's say the first condition. It tells me that epsilon 1 times E10 perp e to power I k1 dot r minus omega t plus epsilon 1 E10 prime perp e to power I k1 prime dot r minus omega t. This should be equal to E20 perp e to power I k2 dot r minus omega t. These are just the components of these E fields perpendicular to my surface. And since they are not parallel to my surface, at least in the case that I am considering, the electric field is not parallel to my surface, these components are non-zero. But you see, we had already used one argument to claim that omega should be the same in all ways. And that argument was this equation should be satisfied at all times. Now, if omegas are different, then we might satisfy this equality at some time, at a particular time, but it won't be satisfied at all times. So that basically tells us that omegas should be the same. For the reflected wave, for the transmitted wave, they should be equal to the angular frequency of the incident wave. Now we have one more condition though. You see, these equalities should be satisfied at every point on the interface. Now before, these factors were just k1 times z, and when we set z is equal to 0, they were just 0. But now, if this equation is to be satisfied not just on one point on my interface, but at every point, k1r should be equal to k1 prime r, it should be equal to k2 prime r, at every point. At every point when z is equal to 0. Otherwise, this equation can be satisfied at most at certain points, but not at every point on my interface. You see, in the previous case, when we had this normal incidence, at z is equal to 0, this was 0. Z is equal to 0, this was 0. When z is equal to 0, this was 0. So no problem. So let's see. Let me just take some origin somewhere. Let me plot my vectors over here. This is my k1. This is my k2. And this is somewhat my k1 prime. I will define some angles. This is the perpendicular direction. Now this angle that k1 makes with the perpendicular, I will just call it theta I. This angle that k1 prime makes with the perpendicular, I will call it theta r. And this angle that k2 makes with this perpendicular, I will call it theta t. Well, setting z is equal to 0 basically tells me that I should choose that r vector somewhere on this plane. You see somewhere over here, this is my r vector. Well, you see here, there's an r vector. R vector is the position at which I'm looking at my electric and magnetic fields. You see, here I have this. I had this condition. This condition tells me that epsilon times the perpendicular component of the electric field at the point r on my surface should be continuous. No. This is z is equal to 0. This is z is equal to 0. Well, yes and no. I already have chosen one reference frame, by the way. I'm working on the reference frame in which this interface separating these two mediums is at rest. I already chose one reference frame. I'm working always in that reference frame. You see, the conditions we drive will be independent of the reference frame. But the interpretation will, of course, depend on the reference frame. You see, the angles, they change from reference frame to reference frame. So whenever we are talking about angles, I will always talk about this angle in the reference frame at which the interface is at rest. Momentum changes from reference frame to reference frame. But in this problem, I'm again considering momentum in the reference frame in which this interface is at rest. My medium is at rest. Conservation of momentum or the boundary conditions, they are valid in every reference frame. But just to be able to talk about some concrete quantities, not concrete numbers, let's say, I'm choosing one reference frame. But that reference frame I already chose when I'm saying that that interface is at rest. And again, just for simplicity, I'm just taking one origin for my I'm choosing a coordinate axis here in a sense. I'm choosing my origin to be this point, and I'm moving these k vectors to this point, just to make it visually clearer. And with respect to that origin, this is my position vector. And there's one thing I would like to warn you about. You see, we will be using such sketches all the time. But this doesn't mean that I have a wave at this point moving in this direction. My wave is everywhere. It's not at that point or at this point. My wave is everywhere. There is one wave which is everywhere. You see, when you do this experiment, let's say, if we could see, for example, the electric fields, the points in which, let's say, the electric field has its maximum value, what we would see is, we will see this. These will be moving in this direction. These will be moving in this direction. These will be moving in this direction. Well, this drawing is kind of a mess. So we just simplify it. So this is my interface. Or you can think of it at every point in space, on the left-hand side, there are these three vectors. K1 is always pointing in one direction, E1 is always pointing in that direction, B1 is always pointing in that direction because we are using linearly polarized plane waves. So that is why I could just move all of them around, pick up some arbitrary point as my origin. And at that point, I also have all those. For the incident wave, there's an electric field, there's a magnetic field at this point. For the reflected wave, there's an incident field, electric field and magnetic field. For the transmitted wave, at that point, there's an electric field, there's a magnetic field. And this condition that I wrote over here should be satisfied at that point also. Now let's see, with these definitions of angles, K1 times R. Well, this is nothing but the magnitude of K1, magnitude of R, times the angle between K1 and R, cosine of that angle, which is pi over 2 plus theta I. You see, this is my K1 vector, this is my R vector. The angle between them is this angle over here. Well, this angle is already theta I, it's equal to this one. Here, this angle is 90 degrees pi over 2. Now, K1 prime dot R, at Z is equal to 0. Well, by the way, this condition that Z is equal to 0, I satisfy that condition by choosing my R vector on this plane. K1 prime dot R is, well, the magnitude is again K1 times R times cosine of the angle between them. Well, this is my K1 prime, this is my R, so the angle between them is pi over 2 plus theta R. And then finally, I have K2 dot R. This is equal to the magnitude of K2, the magnitude of R times cosine pi over 2 plus theta T. And all of these numbers, they should be equal to each other. So basically, that condition over there now means that K1 times, well, cosine pi over 2 plus theta for a general angle is nothing but minus sine theta. So K1 times sine theta I should be equal to K1 times sine theta R, should be equal to K2 times sine theta T. What I did was, well, this R is the same for all of them. So I just remove that R. And minus sign is common for all the terms on that equation, so I also cancel that minus 1. This is what is left. Yes?
Şu K1 prime'ın değerinin K1 olduğunu nasıl anladık?
So let's see, what is K in general? We know that K over, no, K is omega over V, right? So K1 and K1 prime, they are both in the same medium. So they both corresponding to the same velocity, same speed. So V is the same for K1 and K1 prime. Well, omega is the same for all of them. So K1 and K1 prime, they should have the same magnitude, or they should have the same wavelength, since they are in the same medium. Yes, you are getting lost. So where did I lose you? So let's see what we have been doing. Well, the problem with this one is kind of a bit to visualize it. First of all, these plane waves, they are not points. They are just waves that are the same in a plane. So when you go to a sea, you see that all this wave that extends for maybe, depending on the shore, if it's a shore with kilometers long, you will see all these waves that are kilometer long. Well, this plane wave is an idealization of that kind of wave, which is basically the same in one direction, in some directions at least. In this case, it's the same in two directions, but it changes in the perpendicular direction. So that is what we call a plane wave. So they are in one plane, they extend infinitely, and they don't change in that plane. They only change in the other direction. So that is why I'm drawing this picture. So there's all this wave front. So let's say this is my interface between two medium. There's all this wave front moving towards the interface. When the wave front hits it, the parts that hit are reflected. The other parts keep moving and bouncing. The bounced ones will be, this is my incident wave. I send it in this direction. When it hits this surface, it will be moving in this direction. Well, some of it will be transmitted, and that one will be just moving in this direction. Okay, so this angle, basically I can create this angle between the k vector and the interface in two different ways. I can either keep the electric field parallel to the surface or the magnetic field parallel to the surface, still giving an angle to the creating an angle between the direction of the wave and the interface. In this problem, we are just looking at a particular case in which the B field is at rest. B field is parallel to the surface. So that's what we did. So there's this incident wave. It's arriving in this direction. All these points on my wave, they are all moving in the same direction. That is the k1 vector that I'm showing over there. It's not assigned to a single point. That k1 vector is the direction of the motion of all the wave. It's not just at that point. But just for simplicity, I'm just showing it as if it was a point mass at that point. That's maybe probably something misleading. When you look at this picture, the first thing that would come to your mind, okay, there is this point particle colliding with the surface, bouncing back, or maybe just crossing. There is no such point object. The wave is an extended object. Now, as the wave is approaching, this is my surface. The B field is in this direction. It's parallel. But the electric field, it's approaching like this. This is my k vector. This is my E vector, the electric field. And this is my B vector. My B vector is still parallel to the surface. This is the E vector. This is the k vector. And some of it just bounces back. It will be moving in this direction. Let's say the E vector is still in that direction. Okay. In that direction, let's say the B vector will be in this direction now. Of course, it might be the other way around. We don't know. That's what the derivation will tell us. So it's just moving in this direction. Now, again, I repeat, this wave is everywhere. It's just extended. So the wave front collides with my surface at every point along the surface. So if I have boundary conditions, those boundary conditions should be satisfied at every point on my surface at every time. This is quite a strong restriction. It's not just I should have the continuity of the epsilon times E perpendicular component at this point. I should have it at every point. You see, this is this equation over here is the continuity of the perpendicular component of the electric field. So I just wrote the perpendicular component of the electric field on the left of the interface and then on the right of the interface. They should be same at every point on the interface. So this is our continuity. But the problem is, you see, this equation is a time and position dependent equation. And this equation should be satisfied at every time, at every point. To make sure that it is satisfied at every time and every point, I should be able to cancel the time and position dependence on both sides. So I should be able to cancel this exponential on the right-hand side with the exponentials on the left-hand side. That condition I already used, by the way, when I was studying the normal incidence, by assuming that I said that all the omegas are the same, so that I could cancel all the exponentials. Now there's also position dependence in the exponential. In the normal incidence case, there was no position dependence because k dot r, since its k vector is perpendicular to the surface, it just reduced to k times z, and z was 0. So those terms, in the normal incidence case, these terms are all 0. Because k vector is perpendicular to the surface, r vector is a vector on the surface, they are 0. Their scalar product is 0, so that didn't give me any new condition. But now, these products, these scalar products need not be 0 because k vector and r vector, they need not be perpendicular to each other. But that gives me some additional conditions. So I should have this condition satisfied on the surface. The product of k1 and r should be equal to k1 prime times r should be equal to k2 times r on the surface. That is when z is equal to 0. Well, just to show these vectors in a clearer way, I just chose my coordinate axis. Well, I had already said that the plane was the z is equal to 0 plane, so my origin should be some point on the surface. Let's say this is my point on the surface, which is the origin. These are my k1, k1 prime, and k2 vectors. And this is some arbitrary point on the surface. So I just defined these three angles and just wrote the definition of the scalar product. And I know that the three of those three terms should be equal. But at every value of r, at every point on my surface. So that condition just gives me this equality. Now what do those equalities mean? You see, by construction, theta I, theta r, and theta t, they are angles between 0 and pi over 2. That's how I define them. But you see, here I have, just look at this equality. K1s are the same, so I can just cancel them. Sines of two angles, they are equal, and I know that both of them are between 0 and pi over 2. So those two angles should be the same. Angle of incidence is equal to angle of reflection. So whatever the incident wave, whatever angle the incident wave makes with the perpendicular direction, perpendicular to the surface, the reflected wave makes the same angle. But of course in the other direction. You see, if this is my normal direction, this is my surface, this is my normal direction, this is the angle of incidence, this is the angle of reflection. It just goes to on the other side of the normal. But the magnitudes of those angles are the same. Second, k1 times sine theta I should be equal to k2 times sine theta t. Now, k1 is omega over v. K is equal to omega over v, which we can also write as omega over c times n. Well, the advantage of this way of writing it is omega is the same for all my waves. C is the same for all my waves. So omega over c times n1 sine theta I should be equal to omega over c n2 sine theta t. So we have this Snell's law. So basically, Snell's law is just a consequence of the fact that the boundary conditions should be satisfied at every point on our interface. Not just on a particular point, but at every point.
Hocam benim kafama şey takıldı. Şimdi biz dedik ya, işte manyetik alan paralel vektör böyle gidiyor. Ama bu böyle dönebilirdi. O zaman belli bir süre sonra elektrik alan yüzeyi paralel olabilir.
You say, how does it rotate?
Şey etrafında da mı?
How? You see, when we were discussing polarizations, we basically discussed two types of polarizations. One was plane polarized. Now, plane polarized means that the electric field is always in a constant direction. Now, it can be in the opposite direction, it can be get larger, smaller point in the opposite direction, but it's always in the parallel to a constant unit vector. That is what we call a plane polarized. And here we are looking at a plane polarized wave. So the direction of the electric field does not change. And the electric field that I show over here, this electric field, since for a wave, the direction of the electric field is the same at every point, every time for a plane polarized wave, it is that vector. Of course, there is also the circularly polarized light. And in that case, you are right. I mean, the direction of the electric field might change in such a case. So it might have a perpendicular component at some point. It might be have zero perpendicular component at some other point, at some other time. But even that case, we can write as the superposition of two different kinds of waves. Two different kinds of plane polarized waves, which each one of them will have the same constant electric field. And one of that constant polarizations will be like this. The B field will be parallel. Of course, we still need to study the other possibility where the E field is parallel. Well, the methodology will be the same. So we will not repeat it in class. So you know where you will be doing it. Let's say it will be the challenge question. Not the bonus one, but okay, so now we have the Snell's law. You see, Snell's law in a sense is equivalent or analogous, let's say, to our claim that the frequency of the reflected and the transmitted wave is the same. They are analog in the sense that, okay, if they are all the same, then these e to power minus I omega t factors for the incident and the transmitted waves, they are the same, and we can cancel them. So the boundary conditions will be satisfied at all times on the interface. Well, if you use the fact that the boundary conditions should be valid at every point on the interface, not at every time, not just only time, but also point, you get the Snell's law. And although we had derived the Snell's law assuming that there is an angle, there is a finite incidence and transmission angle, we are looking at the non-normal incidence. Well, the Snell's law is valid also for the normal incidence. You see, theta I is 0 if we have normal incidence. So the left-hand side is 0. That tells me that sine of theta t should be 0, so the transmission angle should also be 0. That's already something we used in the case of normal incidence. Now let's come to our boundary conditions. Well, up to now, we didn't really impose the boundary condition. We just said that they should be satisfied at every point to obtain the Snell's law. Now let's say that they should be satisfied. Well, you see, since we have the Snell's law, we also have the equality of the frequencies. This equation well, K1R is equal to K1 prime R is equal to K2R. Omega T is, well, they are equal on both sides, so I can just cancel them. Yes, here we have an epsilon 2. Let me also correct it over here. Or let's just rewrite it, epsilon 1 times E10 perp. This should be equal to epsilon 1 times E10 prime. The perpendicular components are not equal to plus. This should be equal to epsilon 2 E20, the perpendicular component. Well, let's also see how many unknowns do we have. We know that once we determine the electric field, we know the B field. So B field is not an unknown. We don't know the electric field of the reflected wave. We don't know the electric field of the transmitted wave. The reflected wave has two unknown components, perpendicular component and the parallel component. The transmitted wave also has these two unknown components. And these two components, we can also write them as in terms of the magnitudes and angles. So we don't know the magnitude of the reflected electric field. We don't know the angle of the transmitted electric field. We don't know the angle of the incident, the reflected electric field, but we know the angle of the reflected electric field. You see, we know the direction of K1 prime. So that already fixes the direction of E1 prime. So we know the angle of the reflected field. We just don't know its magnitude. We know the angle of the transmitted wave. So we know the angle of E2. But we don't know its angle. Now we know the angle, we don't know its magnitude. So we basically have two unknowns. Because one of them we already determined it. We had four unknowns, the magnitudes and directions. But the angles, the two angles, we had already determined it using the Snell's law. So we are left with two unknowns. So we still need two equations for the magnitudes. Well, this is one of them. Of course, the perpendicular components we can write in terms of the magnitudes and angles. That we will do later on. So let's just keep it in this form. So here is one equation we have. Now the second equation will be from another boundary condition. The second boundary condition, the perpendicular component of B should be continuous. But the perpendicular component of B is 0 on the left-hand side, 0 on the right-hand side. So there's no additional condition from that one. So the first condition, to satisfy the first condition at the top of the screen, this should be satisfied. The second condition doesn't really give us any new criteria. Well, we have this the continuity of the parallel component of the electric field. Well, the parallel component of the electric field will give an equation just like of this form, but we don't have the epsilons. So E10 parallel plus E10 prime parallel, this should be equal to E20 parallel. So this should be satisfied so that this third boundary condition is satisfied. And then finally we have one more condition. The parallel component of the B field divided by mu should be continuous. Well, you see, B field in vectorial form, well, we know that its magnitude is E field divided by V in terms of its magnitude. Its direction is in the direction of K cross E. So this is my B field. So the last condition we have, K1 cross E10 vector divided by V1, the parallel component. Well, sorry. Anyway, let me write it in this form for the time being, plus K1 prime cross E20 divided by V1. I should take the parallel component. This should be equal to K2, so these are unit vectors. K2 unit vector cross, now this is E10, E20 divided by V2. Of course, I also have mu1, and mu2. Again, I should take the parallel component. Well, this vector is already parallel to my surface. So this vector, I shouldn't really explicitly, I don't need to explicitly state that I should take the parallel component, because to start with, we assume that the B field is parallel to the surface. So this is automatically guaranteed. So this is my third boundary condition. Okay, now I might have a possible problem though. You see, we have only two unknowns, but three equations relating these two unknowns. So, one of those equations at least shouldn't give me any new information. So at least one of those equations should be related with the other two equations plus the relation between the angles. Otherwise, I cannot find the solution. The solution just doesn't exist. But we will solve it on Monday.
Hocam şu ilk yazdığımız denklem var ya.
Mm-hmm. Okay. This one.
Bunu Snell's law yardımıyla mı yazdın yoksa?
No. These three equations I derived using Maxwell's equations, not Snell's law. But if I combine these three equations with the Snell's law, I have a problem. I might have a problem. And the problem is, you see, I have four unknowns. I don't know the magnitudes of the electric fields reflected and transmitted. I don't know their directions. So that makes four unknowns. So I need four equations. Well, I already have two equations from Snell's law. And those two equations basically determine the angles. So I have two unknowns that I still need to determine using other equations, not the Snell's laws. So I need to determine the magnitudes of the electric field reflected and transmitted using these three equations. But in general, if you have two equations, two unknowns, you cannot satisfy three equations. You cannot satisfy three independent equations using just two unknowns. for us to have a solution, well, one of them should depend on the other two. So that we don't have we shouldn't have three independent equations, we should only have two independent equations. One of them is redundant. Or in a sense, you can say that we have 5 equations for unknowns. 2 equations from Snell's law, 2 equations from the law of reflection and Snell's law, let's say, and 3 equations from the Maxwell's equations. So we have 5 equations, but for 4 unknowns. Using just 4 of those equations, we can solve for those 4 unknowns, and those unknowns should satisfy the 5th equation. If they don't, we are in trouble. Now, of course, we are not in trouble. We will see on Monday that we can solve these 3 equations for the 2 unknowns. If we solve 2 of them, the third one is automatically guaranteed. Any last questions? So see you on Monday.